This is section 1.4, Continuity and One-Sided Limits. All right, so in mathematics, the term continuous has pretty much the same idea that conveyed in everyday usage. And an informal way to say that a function is continuous at a point, x equals c, means that there's no interruption in the graph of f at x equals c. That is, its graph is unbroken at c. There are no holes, no jumps, no gaps. And so here are three, in figure 1.26, three different ways in which you could have discontinuity at x equals c. These are the first, where f of c is not even a defined point, maybe because you're at that point trying to divide by 0. Or there's perhaps a jump from one where it's headed towards one thing from the left side into a very different thing from the right-hand side. Or perhaps f of c is defined, but there's still a hole, and the limit as x approaches c of f of x is not the same thing as f of c. And so there are three ways in which we can destroy the continuity. It could be that the function is not defined at c. It could be that the limit as x approaches c for f of x does not exist. Or it could be that that limit actually exists, but it's not equal to f of c. So these are the three tests for continuity. Number one, f of c must be defined, must be a real number. There has to be a y value associated with the x value of c. 2, the limit as x approaches c of f of x exists. In other words, as you come at c from the left side and the right side, the function is getting only closer and closer to some real number, L, as x approaches c from both the left and right side. It has to approach a real number, L. Okay, and then the third thing is these two things that exist have to be the same number. That is, the limit as x approaches c of f of x has to be the same thing you get when you substitute c into the function for its y value. That's for continuity at a point. And then for continuity on an open interval, a function is continuous on an open interval ab when the function is continuous at each point on the interval. Now, it's impractical to think about testing every real number from, say, 0 to 10. You can't possibly do so because there are infinitely many of them. And so we will have ways of being able to tell if something's continuous on an interval without testing point for point for point. There are functions that are continuous on the entire real number line, and we'll say that that is a function that is everywhere continuous. All right, so let's consider an open interval I that contains a real number c. If a function f is defined on the interval, except possibly at c, and f is not continuous at c, then f is said to have a discontinuity at c. Discontinuities fall into two categories, removable and non-removable. A discontinuity at c is called removable when f can be made continuous by appropriately defining or redefining f of c. So look at figure 1.27. A has a removable discontinuity, and C has a removable discontinuity. The difference between them is that in part C, f of c is actually defined. It's just not where that hole is. And in part A, f of c is not even defined. However, B, the one in the middle, is a non-removable discontinuity. You might think of this as a function that otherwise would have been continuous, and one point has been removed. And of course, any gap you draw is going to be huge compared to the size of the point that you pulled out. But we don't have an ability to make that gap small enough so that we can still see it and be relatively correct for the size. And in fact, a lot of times we'll show that missing point with an open circle. So anytime you have a removable discontinuity, you will have a otherwise continuous function except for that one point. Um, and anything else, it would be a non-removable discontinuity. So I want to teach you something here that may help with this. Something that I hope you learned actually in a college algebra setting, and I'm just reminding you of it. But if you had a function, let's say that's in factored form, factors to be this. You know that the domain of this is x cannot be 2, because you should divide by 0 at that point. X can also not be -3. And if you cancel out, or remove, if you will, the x minus 2 from the expression by canceling, then that tells you that there's a removable discontinuity at x equals 2. Now, because the removable discontinuity is a point that's been removed, we need to know its coordinates. So it's not enough to say at x equals 2. I want you to say at the point 2 something. Now, you can't substitute 2 into the original expression because that would have you divide by 0. But once you've canceled that out, you can substitute and you'll get the coordinates of the removable discontinuity by substitution into the reduced form of that function. So I hope you caught that I intentionally said when you're canceling, you're removing the x minus 2 factor from the problem, which leads to a removable discontinuity. Anything after you've done any canceling that can happen that makes the denominator turn into 0 will give you a vertical asymptote. And for asymptotes, I always want the equation of the line that the curve is approaching. And since it's vertical, it will be an equation of the form x equals. And in this case, it's -3. So if we were graphing this, let me set this up. I guess I can make some marks on the y-axis as well. Won't hurt anything, I don't suppose. All right, so the vertical asymptote is at x equals -3. The removable discontinuity is at 2 1/5. And of course, this great big open circle I'm drawing is huge compared to the size of the actual point, but that's the best we can do. And otherwise, the graph looks like this. Let me think. Yeah, I'm just trying to make sure I get this pretty close to right. So just trying to make it look as good as I can so that you can actually see what this is supposed to look like. Okay, so there are two discontinuities in this problem. The vertical discontinuity, the vertical asymptote at x equals -3, and the removable discontinuity, that one point that's been plucked out of the otherwise continuous function of a g of x equals 1 over x plus 3. This is, by the way, one that if you look back to the definition of removable, I could redefine g of x to be a function that is x over x plus 3 for most numbers, that is, except for where x is -2. And of course, it naturally can't be -3. I'm saying you can't use um, that point. Well, hold on. Let me back up and say something different because I just messed up. Um, we're going to say that g of x is what we had for f of x everywhere except at 2. And otherwise can be evaluated at 2 using this expression. So this allows us to um, fill in. If we were graphing this one, it would actually fill in that dot and make it continuous. So if we did that, which I'm going to show the part that's different in green, that would fill up this point and make it continuous. And so back where I said, let's see exactly how I said that. I'll use the verbiage that I used before. Well, I can't find what I said earlier. Well, I guess I'm just going to have to let that lie because I can't find what I was thinking of. Oh yeah, in one of the slides it says a discontinuity at C is called removable when f can be made continuous by appropriately defining or redefining f of C. So f of 2 here would be defined so that that would fill in that point. If that can be done, which I just did, then that means that this is a removable discontinuity for sure. I can just define a point at 2 that would make it continuous. All right, so there's that. All right, so example 1, let's look at part A. We're supposed to discuss the continuity of each function. So let's start with A. Now, we're going to make an assumption about domain, that we want to use every real number we can. And the only exception will be anything that's thrown out would make us either divide by 0 or take like the square or fourth or sixth or eighth root of a negative number, because we only want real answers. And so we can't divide by 0 and get a real answer. We can't take the square root of a negative number and get a real answer. So if we look at this one, its domain is everything but 0. So as long as we're not using 0, we're in good shape. Okay. Then, if we use theorem 1.3, and this is a good thing to know, and I sort of mentioned it earlier, that instead of doing point for point for point, we're going to have certain types of functions that we're going to know are continuous. And two of those types are all polynomial functions are continuous because the limit as x approaches c for any real number c of a polynomial function p of x is indeed p of c. So all polynomial functions are continuous for all real numbers. And then for rational functions, remember that's the quotient of two polynomial functions. Earlier I used f of x and defined it as p of x over q of x, but they use r of x, so I'll use that too. For a rational function, which is a polynomial divided by a polynomial, is equal to r of c, except um, any place where the denominator, so let me define what that is, P of C over Q of C, everywhere except for where you're dividing by 0. So there's a little caveat. All rational functions are continuous everywhere except for C values that make you divide by 0, such as in the function you can look at above at x equals 2 and x equals -3. So if you can tell me that you have a polynomial function or a rational function, you can clearly say that it's continuous everywhere except for places that make you divide by 0. So since f of x equals 1 over x is a rational function, so we'd want to make this argument, f is a rational function, which is continuous on its domain, according to that theorem. Is continuous, therefore, for all non-zero real numbers. Okay, so that theorem 1.3 comes in handy because as soon as you can say, hey, this is rational, or hey, this is polynomial, you've actually answered a whole lot of what they're asking us about is continuity. All right, so g of x is x squared minus 1 divided by x minus 1, which is a rational function. So I'm going to go ahead and make that statement. So it is continuous on its domain that is on the interval from -infinity to the disallowed value of x, which is 1, union 1 to infinity. Now, just for the sake of interest, I'm going to go a little bit further than the question asks, and I'm going to factor x squared minus 1 to see if I can tell what kind of discontinuity I have, whether it's removable or not, which is a question you'll probably have to address, so that's why I want to say it now. Because x minus 1 can be removed from the problem by canceling, we would be able to say that there's a removable discontinuity at that value 1, and the y value of that, we'd not be able to get it from the original, but the reduced form of that, 1 plus 1, 1, 2 is the point where the removable discontinuity is. Okay, C. Okay, this time we have h of x is equal to sometimes x plus 1 That's whenever x is less than or equal to 0. And sometimes x squared plus 1 when x is greater than 0. So for non-positive values of x, h is a polynomial function. So h is continuous because it's a polynomial for all reals x less than or equal to 0. Okay? And the argument for x greater than 0 is the same, so I'm going to abbreviate it a little bit. So that's continuous on its domain. Well, it's all reals on the part of the domain we're using. So for x greater than 0. Oh, you know what? I need to back up and say something a little bit differently. I just realized I made a mistake. For any function that's piecewise defined, like this one, where you split the domain into pieces and consider different things happening for different x's, I can't make a claim at the transition point between one and the next with a statement like I've made. So I can only claim that's true, what I said above, for x less than 0. The transition point 0 itself has to be tested individually. So anytime there's a transition from one part of the function to another, you have to test the transition. We can say otherwise it's continuous everywhere, except for maybe a 0. So what we'll have to do for 0 is we have to say, first of all, is, oops, not f, this is function h. H of 0, is it defined? This is test 1 from above. Is h of 0 defined? Well, yeah, it does have an or equal to up there. So that means when we're using 0 as a value, we'll use the upper definition, 0 plus 1, not 0 squared plus 1. And we get 1. Second, does the limit exist? And so to assess whether the limit exists, we're going to have to approach 0 from the left side of this function and 0 from the right side of this function. And see if they're the same to see if the limit actually exists. Okay, so when x is to the left of 0, which is the first one we're dealing with, which one of those two polynomial expressions is valid when we're on the left side of 0? Well, that would be the linear one, x plus 1. And can we do this by substitution? Yes, we certainly can. And so the limit from the left side is 1. Now from the right side, when you're on the right side of 0, above 0, which of those two expressions is the valid expression for h of x? It is the quadratic one, right? X squared plus 1. Since that's a polynomial, we can evaluate the limit by substitution, and we get 1. Since the limit as x approaches 0 from the left side of h of x is equal to the limit as x approaches 0 from the right side for h of x, that implies that the limit as x approaches 0 of h of x, because they're the same from left side and right side, that exists and is 1, the common answer for these two expressions over to the right. So we now have the first two things met, and then the last thing is to say of these two things that exist, the limit as x approaches 0 of h of x, is that indeed equal to h of 0? And it is. 1 and 1 are the same number. So, therefore, h is continuous for x is less than 0, for x is greater than 0, and for x equals 0. So it's continuous for all real numbers. And of course, if we were to graph this, it should be supportive of our work that we've done to prove that it's continuous for all real numbers. So let me set up a grid here. All right, so on the left side of 0, we're graphing the line y equals x plus 1 and including 0. So that'll have a y-intercept of 1, a slope of positive 1, and look like this. Okay. Then, for x is greater than 0, we're going to have the graph x squared plus 1. Well, x can't be 0 for that part, but right up to it, it would be equal to almost x squared plus 1 for x almost 0. And if you push it as far as you can, there'll be an open circle here, completely filled in by the other definition at x equals 0. And that's what's going to make this continuous, is that open circle for the right side is exactly filled in with the closed circle coming from the left. Okay, anyway, that parabola would look something like this. And that is a continuous function. Now, it's possible, of course, that you could have had something that didn't look exactly like that, although it may have had a similar form algebraically. It's very possible that your graph would have perhaps been more like this. This is not the same graph. I'm making this one up brand new. What if it had been x squared minus 1? That's not continuous at 0, is it? So it's because that open circle exactly lined up with the closed circle coming from the left-hand side. That's how we can say visually that we know it's continuous there. Okay, let's see. What's next? D. Y equals sine of x. All right. Now, in order to do this one, we're going to need a theorem to help us, theorem 1.6, the limits of trig functions. Let C be a real number in the domain. You might want to underline in the domain of the given trigonometric functions. for every one of them, such as number 1 is the one we're going to focus on for this question, the limit as x approaches c of sine of x is, by substitution, sine of c on its domain. And of course, the domain of sine of x is all real numbers. And so that implies that the trig function is continuous for all real numbers. Because it's continuous on its domain, is what that implies. The statement, the limit of x approaches c of sine of x equals sine of c, implies that it's continuous on its domain. And its domain is all real numbers. So on the interval from negative infinity to infinity. Okay, and what that implies for you is that you need to make sure that you know the domains of all of those trig functions. So that may be something you need to go back and review from your pre-calculus dealings with these trig functions. Make sure you know those domain statements. All right. Now, we're going to talk a little bit now about, this was continuity on an open interval. Now we're going to talk about closed intervals. To do that, we have to first look at a one-sided limit, which I actually sort of slid in just a few minutes ago. When I did the limit as x approaches 0 from the left side of h of x, up here where number 2 is, this one right here, and the limit as x approaches 0 from the right, which is part of the definition of a limit existing, is that the left and right have to go toward the same thing. That notation, from the left being a little negative superscript and from the right being a little plus superscript, kind of slid that in early so that now I can talk about it. And you've actually had a little bit of an inkling of what that is. So if we're looking at the limit as x approaches c, let's say from the right side only, as long as your function is approaching just from that one side all by itself a value, and we might call that value L for the limit, this one-sided limit can exist. And so if we have a function like y equals the square root of x, as long as we're not taking the square root of a negative number, this will be continuous on its domain, by the way. But the question will be, well, is it continuous really for its whole domain or just for the real numbers bigger than 0? Because at 0 itself, you can't say the limit exists from both sides because there's nothing on that left side. So all we could do is talk about the limit from the right side only is 0. And f of 0 is 0. So this is the limit, which I didn't write all the notation. The limit exists, the value exists, and they're the same number. So this would be continuous from the right. Okay? This is continuous from the right. Okay. And then you could have from the left as well. So this would be the right-hand limit. Let me write this. Right-hand limit, or limit from the right. Those are the two phrases that are used here. I'll write them both down. So as it turns out, to have continuity um, for, for a for an endpoint of, from 0 to infinity, we could only consider 0 from the right side, and claim that this is now, because of all the work we've done, we can claim that this is continuous on the closed interval from 0, closed on the left side, to infinity. So what we're using is the same three-part definition of continuity at a point, is that the limit, no, I'm sorry, got ahead of myself. F of c is defined. There has to be an actual value for substitution of c into the function, which is that right there. 2, the limit from one side or the other. Since we're doing this from the right side, I'm going to continue to use that one, but if I had from the left instead, it's the same argument. Okay, that limit has to exist, has to be a real number. And that's sort of what I was saying here without a lot of hoopla about it. And then the limit that exists from one side of f of x has to give you the exact same number that you get from substitution of c into the function. Numbers 1 and 2 have to be the same number. And so that's one-sided continuity is the test for that. And that's how you get endpoints, whether they're continuous at endpoints or not continuous. So let's look at another example. Let's move to example 2. We're supposed to look at this function, f of x equals the square root of 4 minus x squared. We're supposed to find the limit of f of x as x approaches -2 from the right. Now if you think about it, if we were on the left side of -2, just pick any number like -3. -3 squared is 9. 4 minus 9 is a negative number. We can't do that because it doesn't exist. So we can't explore from the left side of -2 because there aren't any values. So we really have to do this from one side only. So you'd never want to write, for this problem, x approaches -2. Stop. It has to be from the right. So this limit as x approaches -2 from the right of the given function. Now we're going to need a theorem, which I don't have in front of me. Okay, well, it just so happens that for radical functions, we can do limits. We said this, I think, in an earlier session, but the limit of a radical function exists, and you can use substitution as long as it doesn't force you to have the square or fourth or sixth root or any even indexed root of a negative number. So we're going to try substitution here, and as long as our result is not negative, we're good to go. So 4 minus the square of -2. The square of -2 is 4. And so we end up getting the square root of 0, which is a real number, equal to 0. And that's its limit from the right-hand side. Now, as a little bit of confirmation of that, do you know how to graph this without your calculator? It's kind of a cool exercise. Something you should be able to do. Well, you're probably not as good at graphing radicals as other things. So if I make note of the fact that any radical answer I get here will be positive, y will only give me positive or 0 as an answer, I can square both sides of the equation and then get all of the x's, all the variables together on one side, like this. And you say, oh, wait a minute, I've seen that before. That's the equation of a circle. That's the equation of a circle centered at 0, 0 with a radius of square root of 4, which is 2. But we do have to keep in mind we're not graphing the entire circle because we already acknowledged that we can only graph for the original problem y values that are greater than or equal to 0. So we won't get the whole circle. We'll get only the part of it where y is 0 or bigger. Something like that. And as we approach -2 from the left-hand side, you see that that is indeed approaching 0. So the little graphical confirmation of what we just found by substitution. Now, there's another type of function that I hope you saw in pre-calculus and or college algebra. It's called the step function. The most interesting and most often used of those is the greatest integer function, which is this symbol. And you might want to look at the print version of this because I'm not sure you can exactly tell what that's supposed to be, but with my hand-drawn thing. So that's the greatest integer function. And it's defined, let me write this down. This is the greatest integer function, is its name. Anytime something has a name like this, like parabola or circle or something, you probably ought to pay attention to all the named functions. Make sure you know how they're done. So this will give us the greatest integer. That's what this symbol around x does. It gives you the greatest integer n that's less than or equal to x. So to get started on this, let's make a table of values for this, and I'm going to start with positives because they're actually easier. So if I did 0 and 0.1 and 0.9 and 1 and 1.2, I'm just making up some numbers. We're looking at each x and saying, what's the greatest integer that's less than or equal to 0? Well, that's 0. What's the greatest integer that's less than or equal to 0.1? That's 0. What's the greatest integer that's less than or equal to 0.9? Still 0. So this is not the rounding function. Be careful. When x is 1, what's the greatest integer that is less than or equal to 1? That's 1. The greatest integer that's less than or equal to 1.2? Still 1. 1.8? Still 1. Okay? Those are the easiest ones. These others, you're going to have to think about this. You might want to picture a number line or something to help you. Let's do -2 and -1.9 and -1.1 and -1 and -0.4. So -2. What's the greatest integer that's less than or equal to -2? -2. -1.9. Again, think about the number line. Here's -1. Here's -2. And -1.9 is about right there. So what's the greatest integer that's less than, to the left of it, less than or equal to -1.9? That's -2. How about -1.1? which is right there. What's the greatest integer that's less than or equal to that value, negative 1.1? Still negative 2. The greatest integer less than or equal to negative 1? Negative 1 itself. Greatest integer less than or equal to negative 0.4? Still negative 1. So let's see why this is called a step function. See if we can, from these few values we've thought through, plot them and think about what else could happen for all x's that we might want to plot. Okay, so I'm going to plot the points we have and maybe make up some more as we go. When x is 0, graph 0. When x is 0.1, graph 0. When x is 0.9, graph 0. In fact, for everything between 0 and 0.9 at least, you'll always get 0. 0.99, 0. 0.9999994, 0. And that's going to be true all the way until you get to 1. Then all of a sudden, the answer is going to jump up here. 1 gives us 1. And then 1.2 gives us 1, and 1.8 gives us 1. In fact, we continue getting 1 until we get to 2, and then at 2 we'll jump up here. Now to show that these bars, these horizontal bars, go all the way to, say the first one goes all the way to 1 but doesn't include 1, we're going to put an open circle there to say it goes right up to it but doesn't include it. So this will be an open circle. Okay, let's go to negative 2 is negative 2. Negative 1.9 is also negative 2. Negative 1.1, also negative 2. Then when you get to negative 1 itself, it's going to jump up here. And so, again, that bar goes from the left all the way to the point where it jumps, and then you have an open circle, and it jumps up. So this is what that graph looks like. Solid dot on the left end of it, open circle on the right end of each. And if you imagine it, that looks like a stairway, right? You could step on those, hence the name step function. Okay, so let's see how we deal with this for limits. Let's say that we were asked to find the limit as x approaches negative 3 from the right for the greatest integer function. So think about a number as an example for this. Something to the right of negative 3 like negative 2.5. What is the greatest integer that's less than or equal to negative 2.5? What's negative 3? Negative 2.9? Still negative 3. Negative 2.999? Still negative 3. Okay? Then let's look at the limit as x approaches negative 3 from the left. So again, think of examples to get your thinking straight. Something to the left of negative 3 would be something like negative 3.5. The greatest integer value for negative 3.5 is negative 4. Negative 3.1, negative 4. Negative 3.01, negative 4. So this is negative 4. So if I were then to say, what is the limit as x approaches negative 3 for this function? We've done the requisite pieces of figuring that out. We figured out the left-hand limit and the right-hand limit. It's approaching negative 3 from the from the right side, and it's approaching negative 4 from the left side. Are those the same number? Since they're not the same number, this limit does not exist. And to show that graphically would require that I go just a little bit more into this graph and plot this. Oops, I'm going to need one more. I just realized that. Okay, well, my axes don't go far enough, but just imagine. So we're approaching negative 3 from the right-hand side. So negative 3 is right here. From the right-hand side, we're approaching a y value of negative 3, right? And then from the left side of negative 3, we're approaching a y value of negative 4, right? And those are not the same number. And therefore, since we're approaching different numbers from the left and right side, the limit does not exist. Okay. So something I've been saying for a little while now about the limit existing, the only way it can exist is if the limit from the left side and the limit from the right side have to be the same number, which we looked at graphically and numerically a few sessions ago. Now we're saying explicitly that limit can only exist if those are the same number. In this last example, they were not the same number, so the limit did not exist. So please read theorem 1.10, and that's basically what we've been talking about. So as I said earlier, we can extend the idea of continuity to a endpoint of a domain like that square root of x graph that we looked at earlier. We can say that the function is continuous from closed 0 to infinity because the steps I gave here about the one-sided limit existing and that one-sided limit equaling f of c, that would imply that it's continuous at 0 itself from the right side only, and then the rest of it, because it's a radical function and we're not taking the square root of a negative number ever, that it will be continuous on its domain, including 0 now, because we have this one-sided limit. So if you look at a definition of continuity on a closed interval, this can also be applied from the left side instead of the right side. In fact, if you look at figure 1.32, that one is continuous both from the left and from the right. And the way you can tell that is that if it's continuous from one side, as you can see here in this graph I have, well, let me kind of copy their graph. Hold on. Let me just kind of sketch their graph right here so we can all look at it. Visually speaking, it's really easy to tell if it's continuous at the endpoint. If the function goes right up to the value at that place, and you have a closed circle at A, that means it's continuous at that point. And B, same thing. If, however, you had something like this, this one is only continuous at B, not at A. I didn't label A and B, but that's the same kind of points. Okay, so basically you can tell when the graph goes right to a closed dot, closed circle at A or B, then it's continuous at that endpoint of the interval at A and B, which is this picture. And the one on the right is only continuous at B, not at A. All right. So I'm going to need to go to another file to finish this. So I will see you in the next recording.